Okay, so we talked about how a resolver works in a previous video, but today we're going to talk about the CSR, Copley Serial Resolver. So the basic idea is a chip, 15 millimeters by 15 millimeters, with a full resolver to digital converter designed into it. It's designed to be used with the modules. So you mount it on your board. We could mount it on our boards. Can also be used in a cable to adapt from a resolver to a digital drive. Any drive that does BISC or SSI Clock and Data. So the general idea is you send out the excitation, you bring in the sine and cosine, you convert it to digital. You can also bring in some motor temperature, some grounds, shields, and maybe some hulls, whatever you got out there, you plug it in and it goes through through the adapter to the drive. The drive it sends out a clock and receives data back, and also powers the device with 5 volts. However many tens of milliamps it takes to run the processor and drive the resolver. This is sort of a artist rendition of the chip in a cable for an XSJ. We'll take a better picture with the CAD engineer, the mechanical engineer. So yeah, you basically unplug from the drive, resolver drive. You get yourself an encoder drive for less money. You plug your cable in here. It converts it to digital clock and data, and then plugs back into the drive. Maybe there's some little feet here for mounting, or it's small enough that it just, tie wrap it to something. So today's system here, we're going to take a look at the Copley Serial Resolver. So I've got a Xenus here. This is actually a Xenus resolver drive. So I'm doing a comparison of like onboard circuit versus the external circuit. Honestly, I don't see any difference. Improvements come by grounding the motor case and grounding the shield at the drive. And I've got a Xenus edge filter here we'll play with a little bit today. Next time, I just wanted to show you the nano mounting board. So that big motor that I'm driving with the Xenus, next time I'm going to drive it with a nano and a little mounting board and an adapter. The nano mounting board is smaller than the adapter. This thing's going to get smaller. So anyways, let's take a look at the PWM noise. We have to enable the drive. Of course, my drive got a feedback fault because I was hot swapping. That's when you plug and unplug stuff with the power on. Never do that. That's bad for equipment. My drive's going to be fine, but you can see there's a count, plus or minus a couple of counts here with the drive disabled. Okay. And so that, when you're disabled, you're not getting any PWM. When you enable things, you start seeing some PWM. And I got 1, 2, 3, maybe 4 counts. You see the noise on the scope here at a couple volts per division. I got some pretty good noise amplitude here. Well, that's annoying. Anyways, so let's take a look at if we connect up a ground. So now the shield finds a path to earth. I have to try to, So the noise at least gets cut in half. All I did was connect the shield to the frame. It's supposed to come through the cable and connector, but we're missing the connection here. The shield is now connected here, but it doesn't make it out to pin 1, which goes to the drive and gets to earth here by the fact that earth is connected to the drive at the power input. We'll take a look at the same signal here with the filter. I'm going to disable the drive, and then never do this hot swapping business here. It's probably better to turn the power off. That way you know the drive's disabled. I just want to take a look at the improvement with the filter. Yeah, that cut it down, I don't know, it's less than a volt now, half a volt maybe. So significant improvement with the edge filter. Now, part of the problem here is that the case of the motor is connected to the shield at the motor. That's a big no-no. We're not supposed to do that. There's a good path to earth for the motor case, especially when you bolt the motor in. But still, some of the electrons find their way down the shield, and yeah, that affects the signal to noise ratio. Now we're doing probably a little better, plus or minus a couple of counts. So let's take a look at the improvement of the resolver here. Okay, no more fault. I'm going to make a single rev move, try to capture some counts here. So let's zoom in and see left click, drag, drop. So I've got on average a couple of 2 counts here. The quantization, of course, is a count, and we'll look at the resolution, but plus or minus a couple of counts here in a system with good cabling ground, pretty good cabling grounding shielding. We could make an improvement by not connecting the feedback shield at the motor, but we have some pretty good resolution here. The resolution is, we say it's 2 to the 14, but in actual fact, going through the basic setup, we can select Copley Serial Resolver. It's funny comparing the resolver on this drive to using the Copley Serial Resolver. That's the clock and data. So we're just using the adapter here. Same type of resolution. 16384 is the default, but that's because it's less good effective number of bits there. But 65536 is that should be 16 bits. So 2 raised to the 16 and 16 bits of resolution, but plus or minus a few counts. So let's be honest about it. After you put the data in and you enter the feedback information and you calculate the tuning parameters and save to flash, you'll want to do some phasing. I like to use manual phasing. So tools, manual phase. And when I enable this motor, there's nothing attached to the load. So I should be able to spin this motor shaft. And so that's the black needle. I'm just rotating a current vector open loop. I mean, you crank that current up. You can do 5 amps if you want. The important thing is that your counts start going positive when you go in the forward direction, and that the red needle follows. If I had a 30-degree offset here, you'd see it. So I'm lagging by 30 degrees in that forward direction. I'm leading. So I'm gonna correct that here with a little offset, and now I'm tracking. So the red needle is the feedback, and that's tracking as I rotate through the electrical cycles. This is a 6-pole motor. It's got 3 electrical cycles, and I spin the motor, and I can watch it rotate. Let's see if we can do that on the camera there too. So again, just open loop. We're rotating the current vector. See if we can rotate it a little faster. So open loop, rotating the motor shaft and looking through the electrical cycles. So a 6-pole would have 3 electrical cycles. And so we can go reverse direction and check the feedback to make sure the counts are good. Again, when you're disabled, things are looking really good here for counts because there's no noise. But when you enable things, there's some PWM action, plus or minus a couple of counts. And then, yeah, so you got, current loop bandwidth tuning. In this system, it's a slightly larger motor, so not very high VP and VI. And with this larger motor, I set the bandwidth down to 100 hertz single pole. I didn't want more gain than was necessary. I don't like to multiply noise unnecessarily. And this is in anticipation of a larger inertia, so I just cut the PP in half there. Tracking windows are good. I mean, you could bring this down to, like, I don't know, 10 counts and get into the settling window. That would be kind of a normal move. Longer trace time for a single rev, 65536. And we could make a 10 rev move. We'll do it at 1.25 seconds. So this motor is a little bit coggy in there. I could hear it. Oop, longer trace time. So 10 revs, move and settle. Yeah, these bumps are related to the motor phase angle. It's a high torque motor, so it has a little bit of ripple in it. And we'll look at the motor phase angle. And as we go through 1, 2 bumps, 1, 2, oh, there's 4. Yeah, 8-pole motor. Sorry, 8-pole motor. So two bumps per rev, four electrical cycles. 1, 2, 3, 4. You get two full bumps. You turn the gain down. You just smooth it out with some inertia. The interesting thing about the resolver is it is absolute within 1 rev. So on power up, you get like an absolute position, like a north marker. So that's that position here. Spin it back around down to 0. So it's kind of like an index, but not really. It's called the north marker on a resolver. So we can simulate emulated encoder output, and it's just going to wake up in the same position it's in, plus or minus a few counts. So that's how close we're to 0 here. Here's halfway around, 32,768, or 32,000 approximately here. So World War II era technology, cool feature, absolute within 1 rev. Okay, thanks for watching.